Hey guys, in this tutorial we're going to take a look at how we can use data visualization methods in Grasshopper to sort of inform us of what is actually going on with our geometry or our structure or something, to give us a better understanding of, in this case, a kangaroo simulation. So I'm just going to kick this simulation off and restart it so we can see what's sort of going on. So what this sort of does is this mesh has a whole lot of hotspots on it, if you will, that I've assigned a deflection value to. All these blue areas are where we should be getting the most deflection, and the red areas are where we're not getting as much. And this mesh is slowly going to sort of fold on itself, but then inflate into the most stable version of itself. And that's what we're going to create. Alright, so I'm going to pause this simulation and dive into a new document. So we're going to start with a normal sphere as well as a mesh sphere X. Now, you might be wondering what this mesh sphere X is, and we'll get to that in a sec. I'm going to throw down a slider with a maximum value of 100 here, plug in my radius values, and in order to understand what this mesh is, I'm also going to drop down a ordinary mesh sphere with the same radius. So this the ordinary mesh sphere has, I guess, lines of latitude and longitude, if you will, to bring a real world metaphor in to explain that. You know, it's got its sort of directional axes, the vertical and the horizontal, which means that we get a row of a loop of triangles at the top and at the bottom. Now, Mesh Sphere X remedies this by creating a completely quadrangular mesh, and the way it does this is loosely based on the Catmull-Clark subdivision method. If we bring in a mesh box, and actually I'll bring in a center box as well, and give it an X, Y, and Z size, plug it into my mesh box, and then just assign some divisions with an ordinary slider. So my X, Y, and Z. Okay, so if I plug this mesh box in with no divisions across the surface into my Catmull-Clark, you should start to notice something very interesting. If I just preview this mesh sphere off, set this number of divisions to 3, and plug it in. So as you subdivide a box, it will tend towards a sphere, and that's because of the way the Catmull-Clark subdivision works. The shape tends towards a spline along any sort of edge loop, and so yes, this turns a box into a sphere, which is a very common method in other modeling programs. But luckily, we don't actually need to do this method to create the mesh sphere like this in Grasshopper, because we've got the component which does it already. And in fact, it probably does it a little bit better than the Catmull-Clark subdivision, because we have control over the number of divisions in each direction, whereas with the Catmull-Clark it has to be, or would it have to be either 2, 4, 8, 16, or so on and so forth. Alright, so I might just set this to, what, 18, that'll do for now. And what I'm going to do is I'm going to pop 2D, and I'm going to create a region. So I'm going to create a rectangle, and I'm going to give that rectangle maximum value of 1, so it's gonna, this rectangle is basically going to be a my 0 to 1 space with this pop 2D, so that when I evaluate my surface at these coordinates and reparameterize it, it will give me point distribution along the entire surface, whereas I could sort of lower this to give me only points in like the lower quadrant, or I could take as much of the sphere as I want if I wanted to localize it. That's sort of why I prefer to just doing a simple pop geo. While it might sort of give you the same, well, roughly the same result, you know, this has that extra layer of control built into it. So I'm going to set that back up to 1. I'm going to turn this to an integer slider with a maximum value of 100. And this is going to be my number of points in the collection. And somewhere around maybe 16 will do. And then I'm also going to set a seed value. The seed value is just, or basically is just a new generation. So every seed is completely unique. And you can set this value as high as you want or as low as you want. I'm just looking for something with reasonably spread out points across the surface. I'm quite liking that one at the moment, so I'm going to stay with that. Okay, so now what I'm going to do, actually let me just quickly set up the Kangaroo simulation. So we have Kangaroo physics. We have a force object, which as usual is going to be springs. That goes in my force objects. My geometry, actually, instead of plugging in the mesh sphere, I'm going to weld these vertices beforehand. And this is sort of just a preemptive method in case the mesh did decide to do anything funky while passing through Kangaroo. This should remedy that. I'll preview these off. And I'm also going to extract my mesh output on this side. I'm going to plug in a button. And I'm going to plug in a timer. I'm going to set my timer to 20 milliseconds, disable it, and okay, now we can continue setting up the simulation. So, like we always do for our springs, we need the Weaverbird edges, the Weaverbird mesh edges to be more specific, and this goes into my connection. And so now, what I do want to do is I want to sort of drive the length of these edges based on their proximity to each of these points. So what I'm going to do, oops, I'll keep those on for now. I'm going to do a distance between each of these points, and I need to extract some points from these edges. So what I'm going to do is I'm going to do an evaluate curve, and I'm going to set the parameter to 0.5, and I'm also going to reparameterize the curve for good measure. So now when I plug this in, it won't work straight off the bat, it'll just give me a whole list of values, which is why I need to graft this input, so that I get, actually, I want to graft the other input, so that I get, how many is that? 3,888 lists, each with 16 items. And then I can preview these off, and I only want the smallest distance from each of this list, from each of these lists. So basically, it's going to give me the point or the value at its closest, what should we say, its closest reference point, and it will ignore all the rest. So that I'm just sorting this list and using a list item to pull out the smallest value. Let me make some more space again. Alright, and now that we have that, we can flatten this input and we can do a remap. So we're going to remap these numbers based on a bounds. So I'm going to now plug those in, like so. And now we've got what we should need for our data visualization. So I'm going to grab a gradient. And this remap is going to be my parameter value. Now, good thing about a remapping this to a 0 to 1 domain means that I don't need to plug anything into my lower and upper limit because those are already fixed to 0 and 1. And I'm just going to change the gradient type to this one here, because to me it's pretty simple to understand. Blue's your upper, red's your lower. Very simple. Alright, and so now we can reset the simulation so that we've got the mesh feeding through. I can also preview off these edges, and we can set up our visualization on this side. So I'm going to copy and paste these components here, and I'm going to get a geometry preview. Custom preview, sorry. And I'm going to preview all of these points. So this is now this is giving me a deflection value, but you might be picking up on the fact that this is, well, actually you might not, because I haven't explained this, but oh, pardon me. What I do want is I want the most deflection at these points here, and blue is going to be my greatest deflection. So what I'm going to do is I'm going to create an expression. And this expression, you know what, we might still want this result, so I'll work it in as well. What we're going to say is if x equals true, then we're going to say 1, then we'll give it an x value, then we'll return x, otherwise we'll return 1 minus x. So once again, for our conditional statement, if open parentheses our condition, and then if the condition is true and if the condition is false. So if x is true, actually I want if y is true, and my y value is going to be this boolean over here. And so now I can plug this in here, and if I flip this around you can see we're flipping that value. So now what I want to do with this is I want this to control my my spring length. So I'm going to grab a multiplier, and I also need a curve length component. And so this multiplier is just going to sit over here. I'm going to plug my length in, and I'm also going to plug my multiplier in. So now this is driving our simulation. If I hit this button, we can now see we're getting these sort of moments, well, where it's more expanded out, where we're getting greater expansion. We can see we're getting a corresponding blue value, and when we're getting a tighter result, that's where we're sort of getting into these yellow, orange, and red regions. Alright, so next thing I'm going to do is I'm going to bring in a new force object, one that we haven't worked with, and this one is mesh pressure. Now mesh pressure is actually a cluster. It's a custom component that has been pre-built by Daniel Piker when he created Kangaroo, so that you don't need to use the actual pressure component. It just makes it a little bit easier to use. Don't necessarily, I mean, you should have this, but if you haven't dropped the user objects that came with Kangaroo into the correct folder, which is this one here, user objects, and we can see we should have mesh pressure right there. If you haven't dropped those into this file, then you will not have mesh pressure, so just make sure you do that. If you don't, let's just quickly take a look at what this actually is. So these are all old components for Grasshopper from a couple of versions ago, but they all have parallels now. So this decompose mesh is now deconstruct mesh. this vertices component is deconstruct face, and then we have our list item. We also have the pressure component that we just saw, and that's what our cluster does. It just extracts the relevant information to use this pressure component. So I don't need this, I need this. If I plug my mesh in here, and then this force object can now be added into my forces. I'm going to reset the simulation. It's still not going to work because I need to flatten my forces. Very important to remember that. And then we're going to reset the simulation, and let's see what happens. So there we go. We're starting to get a result of sorts. But we can, because we're focusing on data visualization, we're going to look at how we can further modify this. And so what I am going to do at this stage is I'm going to grab a quick graph. And if I just plug this in here, you'll see, okay, it's giving me a whole list of values, which is not incredibly helpful at this stage. So I'm just going to sort the list and then plug it in. And there we go. We get this nice, I don't know what shape this curve is. Could be a modified Bezier curve. Let's go with that. But it sort of peaks and then flattens out in the middle and then spikes again. Okay, so what we can do is we can create an expression to modify the shape of this. So this expression is going to be x to the open parentheses 1 over y, and what this is going to allow me to do is to skew my values one way or the other. Actually, sorry, not x times, we want x to the power of 1 over y. So you can see at 1 we get this exact same curve, but if I reduce this value, we can start to sort of flatten out the shape of this graph, which if we connect these in here and then reconnect this, we can sort of control, we can use this function here to control the range of influence of our of each of our reference points. So if I wanted to have wider influence, I'd drag this up. If I wanted to have shallower influence, I'd drag it down. So we can get it to be very, very shallow if we want. You can see it's only affecting, what's that, the nearest 6 points or so at this level. If I bring it back up to 1, it's got much, much wider control. And now, okay, what I also might want to do is, let me just insert a boolean in here so we can make this expression a little more interesting. You know, we can skew it we could skew it either towards this bottom corner or towards this top corner. So we're going to say if, open parentheses, if z equals true, that's our true condition, and then our false condition is going to be x to the y. What this is actually doing, I should also add, this works quite well with values between 0 and 1, because if you raise a number to let's say to 0, okay, if you were to raise x to 0.5, that is actually exactly the same as taking the square root. And so if we square root values less than 1, then we tend to see, well, actually no, if we just square root values, we tend to see more a shift towards the lower side, which is why this this graph actually works. It's shifting these lower values a lot more than it is the higher values. And then if we flip this the other way, and actually, sorry, I was doing it to 1 over y, so if we did 1 over 0.5, that is squaring the value. Yes, that's now squaring the value, whereas if we set this to false, this is x to the half is square rooting it. And you can see, so now it's got a really huge area of influence. There is almost no red values visible on this mesh. It's all being influenced by the structure. Alright, so that's how the quick graph can help us. I am going to set this back the other way because I do like it when we've got this really shallow influence. So now I'm going to reset it, and alright, what I might also want to do at this stage is work in a cutoff value. So I'm going to create a new expression, and what I'm going to do, okay, we can sort of, if I do play through this this simulation, we can see we get a lot of sort of contraction right here, where these values being raised to a power are really, they're really becoming absolutely minuscule. And so what I do want to do is I want to work in a cutoff value. So I'm going to say if x is less than y, y is going to be my threshold, then we're going to return z. Z is going to be some arbitrary number, probably 1, but it doesn't necessarily need to be 1. So by returning 1, it is going to ensure that the spring remains at its initial length. Otherwise, if it is greater than this threshold, then we want it to sort of explode out. We want it to grow quite a bit larger. So I'm going to say u times x, and then I'm going to close the parentheses off. So we need x, y, z, and u. Y is our threshold, z is our replacement, and then, so that's 1, and then u is our multiplier. So I might just set this to 3 for now, and we'll see how that works. Alright, so I haven't plugged it in yet. I'm not going to plug it into my visualization just because we are skewing that top list of results, so it's going to influence those in a way that I don't necessarily want the visualization to do. So I'll just plug that in, reset my simulation. Okay, and so now we immediately see that our pressure is set way too high. Well, maybe not way too high, but it is higher than it should be. So it's currently 15, I think. So I'll set this to a maximum value of 20, and maybe I'll make it 9.216. And we'll see how that goes. Okay, it's expanding, and there we go, it sort of equalizes. And then it's going to contract a bit. So let me see what I can now do with this simulation. I can expand these, but that looks like it's gonna break it again. So let me pause the simulation. Let me increase the pressure slightly. Reset the simulation. Okay, so obviously we cannot set this this value too high. We'll keep it back to 3. Reset. And it looks like our pressure once again is too high. So this is all pretty delicate, I suppose. It worked around 9, so we'll keep it at 9. and see what happens. Okay, there we go. So it is working. It's all in order. And we're getting these nice sort of pockets or hotspots of data. I might want a few more, so let me just increase this count to maybe 25. And there we go. Okay, so now we've been using this to visualize points. What we could also do is we could use it to visualize the actual mesh. So I'm going to turn this off, and I'm going to grab my mesh. Actually, I'm going to reconstruct it firstly on this base mesh over here. So our data is sort of formatted wrongly at the moment because it's we're driving the process based on the edges, and so in order to color a mesh, we need to color the mesh vertices. And so what I do need to do is I need to deconstruct this mesh over here, and then what I'm going to use is a closest points component. And so from each of these points, I'm going to graft this. I'm going to search for the 4 closest points, because basically every single edge or every single vertex has 4 edges around it, and if we turn on this evaluation over here, we can see this vertex needs to reference the 4 closest points. So I'm going to plug in this value here, and that's going to take a little bit of time to load, but we only need to sort of fetch this data once, because now that we've got our closest point data, we also have this index number. So we can use a list item, and we can list item out of this color. We can take from that index number, and then it's going to give us 4 values, which I'm going to average, and then I'm going to flatten this, turn off my list item, and I'm going to get mesh colors going on this. So I'm going to plug my mesh in here, and I'm going to plug my mesh colors in, and there we go. We now have the corresponding data visible on our new mesh. And I might just apply a Catmull-Clark subdivision on here to smooth out my colors a little bit. Gives a slightly better result. And so there we go. If we reset the simulation, you can see exactly how it works. And there we go. All those nice little hotspots mapped onto our shape, and we have control over, let's see, the influence. That pops up quite nicely. We could expand it or contract it. Oop, but that looks like that's going to break my mesh, so I will just reset the simulation again. What else do we have control of? We could flip this boolean so that it's doing the exact opposite, and we'll have sort of only a few regions of that actual sort of popping of the geometry, because everywhere else is in close proximity to an attractor point. We have control over our mesh pressure. Well, we have very delicate control over that. We could also flip the way this, okay, and that's, okay, that breaks the simulation. So there's a lot of things you need to sort of tinker with to get this right, but in the end there is a lot of cool stuff you can do, and we can use, like I said, we can use this to sort of inform what exactly is going on with our visualization. And if you wanted to, at the end of it, you could actually bake this mesh out with colors. Although I should note, colored meshes can only be rendered in Rhino Render, not V-Ray presently. I believe that is a feature coming in Rhino 6, or if you wanted, you could export this as a, I believe, a VRML file. I'll call it colored mesh, and then when I save it, I need to make sure that I'm using version 2.0 and I'm exporting vertex colors. And so then when I export this, I could bring this into another program like 3ds Max, and I'd have access to my vertex color information. Alright, so that's been a rundown of sort of data visualization for simulation optimization in Grasshopper and Kangaroo. Hope you enjoyed it.